Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to this lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is lecture 3 of Module 1, wherein we are looking for the conductance and its aspects. In our previous lecture, what we have seen the experimental determination of conductance, its other aspects, Ostwald dilution law, Debye-Heckel-Onsager theory, and the numerical based on it. In this particular lecture, we will continue with the further aspects. So now in this lecture, let us start with the point of understanding the variation in ionic conductivity or the conductivity of electrolytes. Particularly, we will see in this particular slide the Vane effect and Debye-Falkenhagen effect, wherein we would like to see the effect of high electric fields. First, we will see the Vane effects. Now, this Vane effect and Debye-Falkenhagen effect, both these effects, they show the evidence that the ion atmosphere exists around the ions and how this ion atmosphere affects the ionic mobility that we have already seen in asymmetric effect and electrophoretic effect. Now, what will happen if I apply the very high electric field? I'm talking about say 10 to the power 5 volts per centimeter or greater than that. So under such situation, an increase in conductivity is observed. Now, why do we observe increase in electrical conductivity, or why do we observe the increase in conductivity of electrolyte? This is particularly due to the fact that at a finite time, or what we can call it as a relaxation time, this particular relaxation time is required for the ionic atmosphere to form around an ion, isn't it? Now see, it is very quite obvious that once the ion atmosphere is disturbed, so it will take some time to develop the other ionic atmosphere around the ion. Now what happens when I apply a very high electric field to it? Under a very high electric fields, the ion moves very rapidly, and since it moves very rapidly, it effectively loses its atmosphere because there is no time to rebuild the ionic atmosphere once again, and as a result there is no time for the formation of atmosphere, and since there is no time for the formation of atmosphere, your ionic motion does not get slowed down. Now what happens exactly in asymmetric effect? In asymmetry effect, your ion moves and there is a drag from the ionic atmosphere. Now since no ionic atmosphere is formed, or there is no time or relaxation time to rebuild the ionic atmosphere, and therefore the ionic motion, there is no retardation to the ionic motion, and therefore ionic motion does not get slowed down. Now due to this, the asymmetric effect, whatever is present because of the ionic atmosphere, that disappears because there is no ionic atmosphere, and that results in the increase of conductance particularly. Now this Lars Onsager proposed the theoretical explanation for the experimentally observed increase in ionic mobility or conductivity of electrolytes, what we say, and that too with the variation of electric potential or gradients of electric potential, and this is particularly known as Vane effect. In other words, if the applied potential is 20,000 volts per centimeter, an ion will move at a speed of about 1 meter per second, say, and will travel several times the thickness of the effective ionic atmosphere in the time of relaxation of the atmosphere. Consequently, the moving ion is essentially free from the effect of ionic atmosphere, which does not have time to build up around it to any extent, and therefore at sufficiently high voltages the relaxation and electrophoretic effects, both of them, will diminish and eventually they disappear, and therefore the molar conductivity will increase, and this phenomena of increase in molar conductivity is known as Vane effect. Similarly, in Debye-Falkenhagen effect, in this effect also the conductivity increases when high frequency alternating current is used. Now this high frequency alternating current is of about 3 to 10 to the power 6 hertz frequency, and under such situation the ion changes its direction of motion so quickly that the more sluggish atmosphere, this ionic atmosphere is that way sluggish in comparison to this motion, and therefore the more sluggish atmosphere cannot adjust and follow the motion of the ion, and this ion moves as if it had no atmosphere, and therefore the conductivity increases. At high frequency, both the asymmetry and electrophoretic effects are absent, and that is what is the observation by Debye-Falkenhagen. In Debye-Falkenhagen effect, the conductivity of electrolytic solution increases whenever the applied voltage has the high frequency. That is the reason basically, and therefore we observe the increase in conductance or conductivity of electrolyte. Very interesting observation. Now similarly we will see the Walden's rule. In this Walden's rule, let us say when a particular ion in solution is subjected to an electric field, it moves with a constant speed, and the ion attains this constant speed when the accelerating electrical force becomes equal to the retarding frictional force. This is also a quite interesting and important observation, that your electrical force, it becomes equal to the retarding frictional force. Let us try to quantify both of these forces, electrical force and the retarding frictional force. So this your electrical force acting on the ion will be given by this mod of charge Z into E, and the frictional force as given by the Stokes law will be 6 pi eta R into V. So where this Ze is the charge carried by the ion, R is the radius, V is the speed with which it moves, and eta is the viscosity of the medium. Now when I equate equation 14 and 15, because electrical force acting on ion is exactly equal to frictional force which is given by Stokes law, if I equate both of them I get this. Now from this we get the ionic mobility. So ionic mobility has a formula that V upon E. So if I substitute these values, I get this equation number 16. So now molar conductivity of the solution is usually given by this lambda. Molar conductivity is equal to nu plus nu minus lambda minus. Lambda plus and lambda minus are ionic mobilities that we know for cation and anion respectively, and therefore if I substitute these values of ionic mobilities, so nu plus Z plus U plus into F for cation, and u minus mod of Z minus U minus F is for anionic, because we know that these ionic mobilities are given by this formula. So using this equation number 16, I can write down this expression for molar conductivity. So my expression for molar conductivity takes the form this of equation 17. So now on the right hand side of this equation 17, if I see, the only quantity on this right hand side of this particular equation is eta, which is varying or which depends on the medium, and therefore for an electrolyte in different medium we must have this lambda into eta, that is molar conductivity into viscosity of the medium. The product of them is constant, and that is lambda into eta is constant, and this particular constant is known as Walden's rule. So molar conductivity into the viscosity of the medium, their product always remains constant, is nothing but the Walden's rule. This Walden's rule is used for solving many numericals wherein we can find out the conductivities, molar conductivities of the electrolyte in a given medium. Let us try to analyze this ionic mobilities, ionic velocities, mobilities, and how we can analyze. Let us try to see in this particular slide. Now let us consider volume Vm. Like this is shown in this, we have tried to show this volume Vm here in this figure. Now let us assume that it contains 1 mole of the substance and it is placed between two parallel plates or parallel electrodes, having one is having positively charged and another is having negatively charged. And let d be the distance between these two parallel plates. Okay. So the electrodes, I also assume that these electrodes are large enough to include between them the whole of the solution. Complete solution is included in between them. Now, in a unit time, the total current flowing through these electrodes is given by this particular expression. Say current flowing through this particular solution is Im is equal to cationic current plus anionic current, and I can substitute their expressions and in the form of this equation number 19, where I have this n plus is equal to nu plus Na and n minus is equal to nu minus Na. We know this. Now since 1 mole is involved, the numbers n plus and n minus will be related to the Avogadro's constant, that is Na, correct? Since 1 mole is associated, and this nu plus and nu minus are respective stoichiometric numbers of cations and anions which are appearing in one molecule of the substance. Now with this information we have to calculate this particular equation, because I can very easily calculate if I substitute all these values over here in this current expression. So I get this, and from this I get this equation number 20. Now I know the molar conductivity of the solution is given by this lambda is equal to kappa upon C specific conductance. This kappa is specific conductance. So if I substitute, this is kappa into Vm volume, and if I substitute it, I can write down like this distance into this area of cross section. I can very easily write down because I know the construction of the volume, isn't it? And its unit is particularly meter square per mole. So observed conductance also I know that this observed conductance is equal to specific conductance into A upon D. So if I substitute, this little rearrangement will give me this particular expression, and this molar conductivity per mole upon D square is the arrangement of this particular observed conductance. So now according to Ohm's law, the current flowing through the solution or the electrodes is given by this I is equal to delta phi upon R, that is potential gradient, upon resistance. So delta phi into observed conductance, obviously I can write down 1 upon R is equal to observed conductance, and therefore my this equation number 22 will imply that this I is equal to gradient of pi delta phi into lambda per mole upon D square. Now on comparing this particular expression and what I can say this particular expression, I get this molar current per mole is equal to I, and therefore this F upon D into nu plus Z plus nu plus or V plus plus nu minus Z minus V minus, and therefore I get this particular expression number 24, that is delta phi into lambda upon D square. Further, I get this from this equation 24, if my solution is infinitely diluted. So if my solution is infinitely diluted, I can use Kohlrausch law for this above equation, and therefore if I use it, I get the further expression as delta phi upon D square into, instead of lambda I can write down this nu plus lambda limiting value of ionic mobility of cation and limiting value of ionic mobility for the anion. Now this value, this particular expression will give me this V plus at infinite dilution is this, and V minus at infinite dilution is this, and therefore I get this equation number 25. Now defining the term of ionic mobility U, and how we will define this term U, let us call this U as the speed of the ion when the potential gradient is unity. So assume the potential gradient to be a unit quantity, and under this unit quantity what we will have, the ionic mobility will be U for cation is this particular, it will give me this particular expression here. So lambda plus at infinite dilution upon Z plus F, and lambda minus at infinite dilution upon Z mod of Z minus into F. Now since my velocity is proportional to delta phi upon d, the ionic mobility may be interpreted as the proportionality constant between the ionic speed and electric field. We can very easily say, since this is proportional to delta phi upon d, correct? And therefore at any other concentration it follows that this U plus at infinite dilution is lambda plus at infinite dilution upon Z plus F, and U minus is this equation number 27. And particularly we can calculate the units of this ionic mobility is meter per second upon volt per meter. So the unit of ionic mobility is meter square per volt per seconds. Now this information I can utilize for the calculation of ionic mobilities, isn't it? And I can determine if I have these values given in the numerical. Let us see in one of the numerical how it can be solved. Let us see the numerical. Say in an example, a potential of 5.6 volt is applied to two electrodes placed 9.8 centimeter apart. That means D is given as 9.8 centimeter. Potential is given as 5.60 volt. Now, how far would an ammonium ion be expected to move in 1 hour in a dilute solution of ammonium salt at 25 degrees of centigrade? And what we are given with this lambda ionic mobility at this lambda is equal of ammonium ion is given as 73.4 Siemens centimeter square per mole. Let us try to solve it. Now we know this ionic mobility is equal to lambda of ammonium ion upon F. So if I substitute this Faraday and this lambda value 73.4 upon 96,500, I get 7.61 into 10 to the power minus 4 centimeter square per volt per seconds. So I get the expression for the solution for ionic mobility. Now I know the potential gradient is given by this 5.60 volts upon the distance, that is delta phi upon d. So if I substitute this value delta phi upon d, so delta phi is 5.6 volt and d is 9.8 centimeters. So I get potential gradient is 0.571 volts per centimeter. Now actual speed can be given by ionic mobility into potential gradient. So my ionic mobility into potential gradient. So my ionic mobility is 7.61 into 10 to the power minus 4 centimeter square per volt per centimeter per second, and my potential gradient is 0.571 volts per centimeter. So I actually get the speed as 4.34 into 10 to the power minus 4 centimeter per second. So once I know that it moves this much centimeter per second. So how far it will move in 1 hour? So what I will have to do? I'll have to take this part and multiply into 60 by 60. So it will give me per hour rate. So it will give the total answer as 1.56 centimeter in 1 hour. Okay, got the point? Another numerical. Say for hydrogen ion and sodium ion, the values of lambda plus at infinite dilution are 349.8 and 50.11 Siemens centimeter square per mole. Now calculate the mobilities and velocities of these ions if they are in the cell in which the electrodes are 5 centimeter apart. D is 5 centimeter, and to which a potential of 2 volt is applied. So we know the potential, that is 2 volt is applied, delta phi. Okay. So my ionic mobility of hydrogen ion is lambda m of hydrogen ion upon Faraday. If I substitute, I get this centimeter square per volt per second. And actual speed with which hydrogen ion moves is ionic mobility into potential gradient. So this is ionic mobility into potential gradient is delta phi upon d. So 2 upon 5 volt per centimeter. So it gives me this 0.001448 centimeter per second. So now ionic mobility of sodium ion again. So I have to substitute this value. Lambda plus value is 50.11 Siemens centimeter square per mole upon Faraday, 96,500 per mole. So I get this this much centimeter square per volt per second, and actual speed will be so ionic mobility multiplied by delta phi upon d. So this into 2 upon 5 volts per centimeter. So I get the actual speed of sodium ion is this. So this way I can find out the actual speeds of say hydrogen ion and sodium ion. Okay. So now when we have seen the ionic velocities, ionic mobilities and their determination, we know that these ionic mobilities, they are always associated with the transport of current in a solution. However, we know that not all the ions transport with the same velocity, and therefore we know that the amount of current carried by each ion is different. Say for example, if I consider the example of magnesium sulfate. So the magnesium ion carry about say 38% fraction of the total current. Whereas these sulfate ions, they carry the rest of the part of the current. Say that is after going 38%, it will give you 62%. So 62% of the fraction will be carried by sulfate ions and 38% fraction will be carried out by magnesium ions. Okay. Similarly, if I take other example of dilute nitric acid, HNO3. So HNO3 solution in the HNO3 solution, the nitrate ions will carry only 16% of the total current, whereas the hydrogen ions carry about 84% of the total fraction. And therefore, it can be seen from this observation of sulfate and hydrogen ion that the sulfate and hydrogen ions, they carry the greater fraction of the total current because in their respective solutions they move faster than the other ions. Now if both the ions in solution move with the same speed, each of them they would transfer the same quantity of electricity in a given time, say whatever it is across the any fixed plane in the solution. However, when we know that the speeds of two ions are not the same, since their speeds are not the same, and therefore in a given period of time, the faster ion will carry the greater fraction of the total current, and the slower ions will carry the lower fraction of the total current, isn't it? Faster will carry the higher fraction and slower will carry the lower fraction of the current. And therefore we can derive the relation between the fraction of current carried by ion and its speed. This will be very important while solving the numerical of the electrolysis. Now when the electric potential is applied to electrolyte solution, electrolysis of the solution starts, we know. The ion starts moving towards opposite electrode where usually they get discharged. Now although the velocities of cation and anions are different, the number of cations and anions discharged, they will be same. And since they will be same, this solution will keep its electrical neutrality. That is the principle. We can understand this phenomena by considering the electrolysis here in this particular figure. Say consider the electrolysis of solution between two platinum electrodes. Now let us say we call this as platinum electrode, this as platinum electrode. Let us say this is anode, let us say this is cathode. Now why platinum? Because it is inert. Now let us assume that this solution is divided into three compartments. What are these three compartments? Anodic compartment, cathodic compartment, and central compartment. Now let there be certain cases. We will classify the over in order to understand the phenomena of this electrical migration of the ions and the conduction of electric current. Let us understand several cases over here. Say case 1 is in absence of electric field, let there will be 4 cations and 4 anions present in each of the compartment. 4 cations, 4 anions, 4 cations, 4 anions, 4 cations, 4 anions. Okay. Since it is no electric field is applied, it will remain the same. Nothing will happen. It is as it is case. Okay. No electrolysis is taking place. Now let us assume the second case. In this case too, let the cation is be stationary, and let its speed be denoted, velocity be denoted by u, that is u is equal to 0, and anions are moving with velocity v is equal to 2. Now say in a unit time, two anions migrate from cathode compartment to anode compartment. Cathode compartment to anode compartment. Now what will happen? As a result, there is a fall of concentration of anions in cathode compartment by 2, while there is increase in concentration of anion in anode compartment by 2. Correct? So the concentration of central compartment will remain same in this case, and two excess anions are discharged at anode and two excess cations are discharged at cathode. Got the point? Similarly, if I consider case 3, now let the cation and anions are moving with the same speed in case 3, that is u is equal to 2 and v is equal to 2. Okay. Now in this case, two cations move from anode compartment to cathode compartment and two anions from cathode compartment to anode compartment. Okay. And therefore, there are excess opposite ions in the concentration in the each compartment. Look, you can see here 6 cations, 6 anions are present over here. Correct? So they will be discharged at those electrodes here and here. Okay. And the central compartment, it remains unchanged. It will be remaining same. Okay. Similarly, let there be fourth case wherein the anions are moving with double speed as compared to cation, that is u is equal to 1 and v is equal to 2. Now in such case, there is excess anion concentration of 3 in anode compartment and excess cation concentration of 3 in cathode compartment. Correct? They will be discharging at those electrodes respectively. So the concentration of central compartment is again the same. Okay. Now from all these cases, all these observations, we can make certain conclusions. Firstly, we can make the conclusion that the number of cations and anions discharged at both the electrodes are always equal irrespective of their speed. Correct? Similarly, second conclusion is that the concentration in the central compartment will always remain constant whatever is your case. And the third one is the fall in concentration around any electrode is directly proportional to the speed of the ion moving away from it. Correct? And therefore, The fall in concentration around anode is proportional to speed of cation. Fall in concentration around cathode is proportional to speed of anion. If I take their ratio, fall in concentration around anode to fall in concentration around cathode is nothing but speed of cation to speed of anion. That is what is the case. Okay. So friends, we will stop in this lecture 3 of module 1 here. We will see the further aspect of migration of ions whenever the electrodes are attackable in our next lecture. Thank you.